All right, so the next 3 videos are actually going to take me quite a while to do because they are the 3 titration problems. So again, I handed out a sheet to you guys saying that there's 3 kinds of titrations that we'll see. There's strong acid, strong base, and then the 2 weak strong combinations. Weak acid, strong base, strong acid, weak base. We're never going to see the weak-weak combination, at least not here in general chemistry. So looking at our review sheet, right, after we dealt with qualitative and quantitative aspects of buffers, the next main theme is thinking about qualitative and quantitative aspects of titrations. And what I hope you see after I put up this series of videos is that titrations are really just the buffer problems, but incorporating volume change and having a species that we have in our Erlenmeyer flask that we call our analyte, and then a material that we add from a burette that we call our titrant. And so we need to think about what happens with the chemistry with those, and at some point the chemistry is going to be such that we reach stoichiometric completion, which we call the equivalence point, and then we'll have to evaluate where we're at. There's 4 places that we can be at in our titrations. We'll be before we begin, before the equivalence point, at the equivalence point, or after the equivalence point. So we'll do with all of these problems kind of some qualitative analysis before we actually go through the quantitative calculations part. So again, just to give you a preview of the 3 kinds of problems that we'll work on. We'll have pH during a strong acid, strong base titration. And again, all of these are going to have 4 points: before the titration begins, before the equivalence point, at the equivalence point, and after. So we've got strong acid, strong base that we did as an in-class problem. We're going to have a weak acid, strong base, again with the 4 different points that we did. That was sample problem 19.4. And then kind of as a complement to that, we did the other weak strong combination, a weak base, strong acid, again 4 different points. So we'll work through all 3 of those kinds of titrations, and for each of them we're going to use this same worksheet system. We'll ask questions about who's in solution, what's the chemistry that can happen, what's the volume change that occurs, and again this is the new piece that makes buffers different from titrations, is that we will have a volume change because we're mixing 2 solutions together. We'll think about any relevant equilibria that are available. And then at the end of the day, we usually need to calculate pH. So we'll talk about how you can calculate pH, when you can use the Henderson-Hasselbalch equation, and so forth. So again, the first problem that we're going to go through is the strong acid, strong base. And a couple of things to point out. This is actually the simplest of the titration because you will always only use ICF tables. There are no ICE tables with strong acid, strong base titrations because there's no weak counterparts that we have to think about equilibria for. So one of the first things that you got to make sure that you're very competent in is just looking at molecules and asking, well, what kind of a molecule are you? Are you a strong acid? Are you a strong base? Weak acid, weak base, because that dictates the kinds of chemistry and the kinds of equilibria that may or may not be at play. So the first problem that we'll work through is strong acid, strong base. And again, we'll go through these 4 different points before the titration begins, before the equivalence point, at the equivalence point, and we'll kind of show you that there's no calculation you need to actually do. The pH at the equivalence point of a strong acid, strong base is always going to be 7. And then after the equivalence point. So I'll kind of keep coming back to this sheet as we go through these points to kind of summarize the relevant calculations that we have here. All right, so again, I'm going to use these worksheets as we go through this strong acid, strong base titration. All right, so part A here, before the titration begins, we're going to have the titration of 40 milliliters of 0.1 molar HCl. So again, just to kind of orient us, this is what's in our flask. This is what we call the analyte. We're talking about adding sodium hydroxide. So we talk about adding sodium hydroxide. This is a substance that's in our burette. We usually call this the titrant. So what's in our flask is our analyte. This is going to be a fixed volume. And the burette, what's the titrant, is we're going to be adding various volumes. So we're adding 0, 20, 40, or 50 milliliters of this sodium hydroxide. Okay. So again, if I think about, and we're going to pull up these sheets here, we think about who's in solution for part A. All right, so we need to think about who's in solution. Well, we haven't started the titration, so the only thing that we have is a flask that contains 40 milliliters of 0.1 molar HCl. So who's in solution? Well, it says that there's HCl in solution, but we need to remember that HCl is a strong acid, so what we really have in solution is H plus and Cl minus. Cl minus, again, is a spectator ion in terms of pH calculations, so we're not going to be concerned with it. All we really have is H plus, and they tell us that we have a 0.100 molar solution, and we have 40 milliliters. So there's no chemistry. There's no chemistry that's happened because we haven't started the titration. No volume change because we haven't started the titration. We never see ice tables with strong acid, strong base. Remember that, okay? Never using ice tables with strong acid, strong base, okay? So really, the only thing that we need to consider is the fact that we have a solution where the H3O plus concentration is equal to 0.100 molar. All right, if we know what the H3O plus concentration is, negative log of 0.1 will give us the pH, and in this case, that's equal to 1.0. So I kind of wasted a piece of paper on this, but I want to use these sheets so that you can see sometimes it's a fairly simple thing, or with other problems, it'll get a little bit more involved. Okay, so before the titration begins, the pH is simply equal to the negative log of the initial acid concentration. And that's what this cheat sheet tells us here. At point number 1, before the titration begins of a strong acid, strong base, the pH is simply equal to the negative log of the initial acid concentration, which in this case was 0.1 molar. Okay, part A. Part B. So now we started doing our titration. So we've added 20 milliliters. We know we're before the equivalence point, and let me just see if I can walk through this to make sense for you guys. With this problem, it's pretty straightforward because we have equal concentrations of both of these species. So if we have 40 milliliters of strong acid in our flask, the burette has the same concentration of the strong base. So hopefully it makes sense that the equivalence point will actually be when we have the same volume of that. We'll actually go through a calculation in just a little bit to actually talk about how to figure out where the equivalence point is. Okay, but at this point, they actually tell us that we are before the equivalence point. So let's go through now and still answer these same questions. All right, HCl in solution, right? We know we've got H plus in solution, Cl minus in solution. Cl minus doesn't matter. We've got 40 milliliters of 0.1 molar. And I'm just going to drop my zeros off here as I write things. Remember that we've got a lot of significant digits there, but just to keep writing simple here, I'll do that. So we've got this guy, again, in our flask. In our burette, which we are now going to be adding to our solution in our flask, we've got sodium hydroxide, which all sodium salts are soluble, so it really breaks up into these ions. Okay, so again, sodium ions are going to be spectators. So here's our 2 spectator ions that we don't need to be concerned about. Our OH minus concentration is also 0.1 molar, but we've added 20 milliliters. So again, this is what's in our burette. But as this tells us here, we not only need to list concentrations and volumes, but we need to list numbers of moles. Okay, so to get numbers of moles, we've got 0.1 moles per liter times 0.04 liters. 0.04 liters. So that tells us that we have 0.004 moles of H plus. The same kind of a calculation here gives us 0.002 moles of OH minus. Okay. So maybe one of the things to kind of remember for chemistry with strong acid, strong base, is the only things that we have in solution that will be participating in any chemistry are H plus and OH minus. So the chemistry is H plus OH minus. Chemistry equations are always drawn with a one-way arrow. Gives us H2O. Okay? Chemistry we show with ICF tables. ICF tables need to use moles. If I'm going a little bit quickly through this sheet, you might want to go back and look at the buffer sample problem, 19.1, because I go through a little bit more slowly how we use these worksheets. So H plus, again, we're going to have 0.004, OH minus 0.002, and water, again, we're going to assume that we have 0 here again, but this is really not applicable for what we're considering. OH minus is going to be our limiting reactant, which means it gets completely used up. We use up the same amount of H plus. Our limiting reactant should always disappear, and we have left over 0.02 moles of H plus. Now again, this is the key difference between kinds of problems that we did before, either with buffers or just kind of some chemistry problems like in sample problem 19.1, is we do have a volume change to consider. So if our chemistry involves mixing substances that create a new or larger volume, we need to add these volumes together and consider that new volume to calculate new concentrations. So we had 40 milliliters in our flask. We added 20 milliliters from our burette, which means our new volume is 60 milliliters. So what this really means is there's only one species that's kind of relevant and remaining at after we add this 20 milliliters, is we need to take this 0.002 moles of H plus and say that it's in 0.06 liters of solution. That's equal to 0.033 molar. Again, that's equal to the H3O plus concentration. There are no ice tables when we have strong acid, strong base. So do not write one. So we can completely skip this next part. And since we know the H3O plus concentration directly, the negative log of that concentration is going to equal pH. So this problem equals 1.48. So coming back to our cheat sheet here and kind of seeing what it says, when we are before the equivalence point, we need to use an ICF table, which is what we did here. We used an ICF table to determine the moles of H plus remaining. Now in this case, this problem, as we've shown, shows a volume of sodium hydroxide that we've added into a flask containing H plus. So before the equivalence point, there's going to be H plus left. I want to say don't get confused if we had something where we had OH minus, sodium hydroxide, in our flask, and we put H plus into it. Okay? Keep that in mind. That could be an exam question where you see something like that. In that case, our titration curve will look like this. All right, using an ICF table, we want to determine the moles of H plus remaining, right? It's just whoever was not our limiting reagent. So in this case, it's H plus that was remaining, divided by the total volume, which is what we did here. And then that gave us H3O plus. So the pH is then going to be equal to the negative log of the H3O plus that's remaining, which is really the acid that's remaining. And we'll get pH from that. So again, before the equivalence point, that's like this point here, which for this problem, 1.48 truly is this point that we have here. All right, so this was part B. Part C, we are at the equivalence point. Okay, when we know that we have a strong acid and a strong base, I don't even need to see a calculation as long as you show me an understanding. But let's just kind of talk about what's going on here. What we truly have is H plus and Cl minus, right? Cl minus, spectator ion, 40 milliliters, 0.1 molar, which means we have 0.004 moles. Na plus and OH minus, spectator. (40 milliliters, 0.1 molar. 0.004 mole. I'm going to show you a chemistry table, okay? But I want just to prove to you why you can say what we can say here. Chemistry, right, between H plus and OH minus gives us H2O, ICF, we have stoichiometric amounts of each of these. So they're kind of both the limiting reagents because they're the same. Both of them are the limiting reagent because there are none left at the equivalence point. pH is equal to 7. So you could do a chemistry table and just kind of say, hey, there's nothing left, pH 7, or there's no calculation that's really necessary at the equivalence point. So if we kind of look at this cheat sheet here, point number 3, when we are at the equivalence point of a strong acid, strong base titration, the pH is always 7. Okay? We noted that when we had equal concentrations and equal volumes, that meant we are at the equivalence point, right? So the volume to the equivalence point won't be equal, though, if the acid and the base concentrations are not the same. So just to kind of show you an example here, this was from quiz 8, right? So this was the quiz on chapter 19. Here we had the titration of a strong base and strong acid. Okay, so in this case we had titrating, here we had the sodium hydroxide that was in our flask and we titrated it with the strong acid. And what we needed to see here is we wanted to calculate the volume to reach the equivalence point. So if we had two concentrations that weren't equal, we had a smaller concentration of H plus than we had OH minus. If we knew we had 50 milliliters of this guy, because this concentration was less, the calculations allow us to see that we actually need a slightly greater volume to reach the equivalence point, again, where we have equal numbers of moles of these. So if you need to, go ahead and take a look at that quiz. The key is posted online just to kind of see how you perform a calculation to see where the equivalence point is if you don't have equal concentrations. So I don't even need a calculation for at the equivalence point of strong acid, strong base. So at the equivalence point of strong acid, strong base, pH will always be equal to 7.0, kind of a definition. All right, part D, last part of this titration problem. After the equivalence point. Again, we're going to treat these problems all the same. I apologize if this is super boring and repetitive, but I want to make sure that everybody sees kind of what's going on here. HCl and NaOH, spectator, spectator. 40 milliliters, this is what we started out with in our flask, 0.1 molar, which means we have 0.004 moles. Hydroxide, 50 milliliters, still 0.1 molar, so it's 0.005 moles. If we write ourselves, and it was, I have 60 on my, so I'm going to change that. I have 60 that we worked through in class. So let me actually just go ahead and change this so it matches what we did in class. 60 milliliters, 0.006 moles. The chemistry for strong acid, strong base titration is always just this. Now what was in our flask is our limiting reagent. That is going to run out first. And what we added from our burette is going to be what's left over. Okay, so again, going through this fairly quickly. Hopefully we've, if you need to review, you can kind of go back to some earlier calculations. So we started out with 40 milliliters. We added 60, so that gives us 100 milliliters total. We only have one species left at equilibrium. I shouldn't say equilibrium. Apologies for that. We only have one species left after the chemistry has finished. So the new concentration of hydroxide is equal to the number of moles that's left in the total diluted volume that we have. So this is equal to 0.02 molar. Again, that 0.02 molar is equal to the hydroxide concentration. So POH is equal to the negative log of 0.02, and that's equal to 1.70. So pH is 14 minus POH, and that's equal to 12.30. So again, never any ice tables with strong acid, strong base. If you know who you have in solution, it can make your calculations a little bit easier. So kind of mapping this on to our last point here on our cheat sheet. After the equivalence point, again, use an ICF table, which is what we did. Use an ICF table to determine the moles of our titrant, in this case hydroxide in excess. Divide by the total volume, which is what we did here. And because our titrant was in excess, and our titrant was sodium hydroxide, our excess titrant is going to be hydroxide. So when we take the negative log of that concentration, it will give us POH, and we need to convert that using this equation to pH. Okay, but we can see that that's this point all the way up here. Before we started low pH, started our titration, slightly increasing pH. pH will always be 7 with a strong acid, strong base at the equivalence point. And past the equivalence point, the pH is determined by the excess concentration of titrant, in this case hydroxide, that we've added.